All right, starting the stream. I'm going to keep hitting refresh until I can see it on YouTube, and then we know everyone's getting it. And then we'll get started. Usually a 30-second delay here. Oh, I can see us. We are there. I'm also going to mute it so you're not getting a duplicate in there. Hello, welcome everyone to Starry Nights. We're so glad that you're joining us. And you know what? We're joining you from the same place that you are because both Indra and I are at home. We're at home too. So this baby can be controlled by remote, which is super cool that we can remotely control the whole observatory. So we're at home experiencing space with you in the comforts of our own places as well. My name's Matthew.
Hi, I'm Indra. You can also
And
call me Indira. Sorry.
yeah, and here we are live with space. So we've got a couple targets for you tonight. A couple things that we're should know ahead of time in terms of struggles that we might have for this evening. So number one, it looks like weather is saying that clouds might start rolling in the next hour. So we're hoping that things stay clear so we can keep looking up in the sky and see what's going on out there. But also we've got the moon that we're dealing with right now. And so the moon is really bright. So we have a couple targets that we're looking at that are a bit fainter. It might be harder to see some of them with the brightness of the moon right now. So we might be fighting with that as well. So, but we'll try and see what happens. So, all right. I have one of the objects that we're looking at right here. And I've got it faint just to start with because I wanted to do more of a reveal. But Indra, what are we doing for our first target?
Yeah, so we're looking at, I don't want to spoil it here. I
No,
wanted to do kind of a nice reveal.
I'll make it
We're
brighter. Here we
looking
go.
beautiful. Yes, we are looking at arguably one of the prettiest planets in our
Oh,
solar
get bright.
system. It's definitely my favorite. We're looking at Saturn. So there we go. Yeah. Um, I always love it when we look at Saturn. I feel like Saturn is such a beautiful planet, and it's also super. I don't know. I always say this, but Saturn is really like 3D looking because you can kind of see like the space behind the rings and space in between the rings, and so I always enjoy looking at Saturn. It's always a treat.
Saturn's kind of low on the horizon right now, so we're at this time, so we're getting a little bit of some. I'm seeing some atmospheric distortion here, a little bit on Saturn. But yeah, Saturn's rings are cool. I was talking with some students the other day who were at the H.R. McMillan Space Center, and we were all mentioning how Galileo made notes of seeing Saturn through his telescope. One of the first people to look at the sky and mentioned that Saturn's rings looked like it had ears sticking out of the side of it. And planets are notoriously difficult to image. So even here, you can see the video of the planet, and it's like distorting and twisted and sort of in and out of focus. And that's because planets are actually relatively small in the sky, so they're really impacted by any motion of the atmosphere. So when you see pictures of the planets that are like really, really crisp or really, really sharp, they're usually imaged with a special technique called lucky imaging. And you'll notice here that we have a few moments where we're lucky enough to get the planet where it actually looks like it is in focus, like right there, for example, and then it kind of goes out. So what lucky imaging does is it literally makes a video of the planet like we're doing now, and then astronomers or astrophotographers will take out those few frames where the planet is in focus and usually layer them together, and then you'll get a final version of the planet that looks clear. But as you're seeing, a lot of the times it's sort of like looking at it through water. It's sort of like jiggling around all over the place. Indra, why does Saturn have rings instead of other planets? What's going on here? What are the rings of Saturn?
Oh, that's a great question. So, Saturn has rings because I think they're kind of the bits and pieces of what used to be a moon, I believe. And I think that moon got a little bit too close to Saturn, flew a bit too close to Saturn, and basically kind of got ripped apart. And so its rings are kind of made up of all these, little chunks and a lot of ice as well. But those rings are actually relatively new. Like if the dinosaurs could have a telescope and see up in the sky, then they wouldn't have seen a Saturn with rings, which is kind of interesting to think about. So on the cosmological time scale, these rings are pretty new. But yeah, that's why Saturn has its rings. But other planets also have some rings as well. They're just very, very faint, I would say. Like Jupiter has like a ring, but it's very, very faint. Uranus also has a ring, but it's very faint. But yeah, Saturn's got the biggest, brightest, most beautiful rings out of all the planets in our solar system.
I'm trying to imagine now what it would look like for a dinosaur to try to use a telescope. Like, can you imagine a T-Rex with its really tiny arms trying to manipulate technology? I think that would be hilarious. Um, and we got this program for those of you who have a chance to also visit our kind of I want to call it our sibling, our spirit kind of like spiritual kind of sibling over at the H.R. McMillan Space Center. We've got one of the shows where we actually fly through the rings of Saturn, and it shows the debris. It's actually all simulated in the planetarium. But I think some of the coolest pictures that we've taken in space actually are from Saturn up close with the Cassini probe. I'll bring one of them up here because there's one that's really, really neat. And I had it for a while actually in a poster on my wall. And it has the rings and Mimas in the background. Mimas is one of the moons of Saturn. And you can see it sort of, Cassini has taken this picture. If I can find the one I was looking for.
If I can just interject here, I'd love to talk
please.
about Cassini and a different moon of Saturn. That's a very interesting looking moon. Yeah, so Cassini did a lot of work with I believe it was Enceladus, and it actually looked at what the heck is going on with Enceladus, because it was kind of a interesting moon. It looks like it's just a big giant snowball. But underneath it, there's an ocean, which is really interesting. And so the Cassini spacecraft kind of flew by Enceladus to take a look at what was going on. And actually, it flew through some of the plumes that Enceladus kind of lets out. It's got these like geysers. And so it flew through these geysers. They spit out like liquid water, I guess, and detected some minerals that are favorable for life. So Saturn itself is very interesting, but its moons also are kind of a point of interest, I would say.
Yeah, isn't that incredible that these moons have like, some of them have twice as much water volume than the entire planet Earth does. It's just like these big floating oceans out there in space.
Yeah.
In fact, Enceladus that you were mentioning, that the plumes from that moon end up in the rings of Saturn. So some of the rings of Saturn are actually made of ocean water from these moons. This is the image you were mentioning. Mimas earlier. Mimas is also sometimes called the Death Star moon because of the big meteor impact that you see on it. It kind of looks like that big dish from Star Wars of the Death Star. But the picture I wanted to show is this one here. We're actually looking at the surface of Saturn. This was taken by the Cassini mission. The rings are here in the foreground, and then Mimas is the tiny spot up here. And this kind of texture on the surface of Saturn is actually shadow that is falling on the surface of the planet from the rings in the foreground. So Saturn can actually have kind of a bluish appearance a little bit too, depending on what angle you're looking at it and how the light is falling from the sun. But yeah, a little bit about Saturn. And we started with Saturn earlier because Saturn is already starting to get pretty low on the horizon early in the evening, and we wanted to look at it before we lost it.
Yes.
All right. Shall we move on?
Yeah, I guess so.
All right.
Sure. What was the next topic target that we had in mind?
I think we're looking at a globular cluster. So in this case, Messier 13. So our software that we use to control a telescope, if you haven't been on one of our live streams before, is literally a whole map of the sky. And the software is literally called The Sky. And so this is the sky on the software. Right now you can see that we are pointed at Saturn. The kind of grayed out area around where we're pointed is actually the roof of the telescope. So that's the dome around the telescope that you can see in the bottom left video. We have the internal camera on the telescope, so you can kind of see the edges of the dome there. And where it's clearer here, this less grayed out area is where the roof is open. So that's where we're actually able to see through to the sky. And literally all we have to do is queue up a target. So I'll type in an object, like if I type M13, the telescope will, and the software that's controlling it just knows where it is. and it will locate the object in the sky. So we'll see now that it's over here and is located where it is. It's sometimes this cluster is known as the Hercules cluster because it's in the constellation of Hercules. It's also known from the NGC number, which is called a New Galactic Catalog, 6205. And then I just hit go, and the whole telescope will move. And so for a really big telescope, it's actually quite simple to use. If you've used a backyard telescope, you'll know that sometimes finding those objects in the sky and trying to point to them can be quite complicated. But literally, we point and click, and the telescope will bring us where we want to go.
Yes, us kids these days, we're very lucky with all of our technology.
We're so spoiled. Yeah, there's a lot of members from the Royal Astronomical Society that will volunteer their time and bring their telescopes up outside when we're doing Starry Nights in person. And those people with their experience of using telescopes for decades and decades and decades, and many of them have the night sky almost like completely memorized, which is really fascinating.
Yeah,
All right.
that's really impressive. I still use my apps basically, like to find objects in the sky when I'm out using my own telescope, just because I do not have the sky memorized. But definitely using your own personal telescope is arguably more difficult than using this one here at the Trottier Observatory. So, yeah.
All right. So what we're doing now is we're opening up something called a live stack. And so in astrophotography, we're always kind of like fighting with the number of photons, how many droplets of light that we're getting from space. And for an object that's really bright, say, for example, Saturn, Saturn is bright enough that we could just point the telescope at it and we'll get almost like a live view of that object. But for things that are farther away in space and more faint, what's necessary for us to do is to point the camera and kind of like take one very long exposure. In this case, what we're doing is 20-second exposures of an object, and then we layer them together like one big sandwich. We call that a stack. And so what we've done now is we've set the camera so it's taking individual 20-second exposures. And we've got the first one in right now, and already we can start to see this star cluster. You'll notice that it's like a big glob of stars, and that's because it's known as a globular cluster. And I'm going to play with the color here a little bit because it's looking a little bit red. So I'll pull the red down a bit, and then should have more of like a clearer image here.
So I believe this is one of the largest globular or just clusters. It's one of the largest and oldest. Is that correct, Matthew?
Yeah, it's so we have these big clusters that are around our galaxy. I'm actually gonna one of the things we can do is trade off resolution for brightness a bit. And I think because this object's so bright, I might be able to go a little bit higher resolution, a little bit more clarity. But you're right. Yeah, these clusters are ancient. And so they orbit our galaxy like moons, basically blobs of stars that we see orbiting around the center of our galaxy. Some of them are really far away. This one's anywhere between 25 to about 30,000 light years away. So this is quite far away from us. And they could have anywhere from, say, a few hundred to several 100,000 stars inside of them. So these are like really, really dense, far denser than the stars would be in our region of the galaxy.
Yeah, I feel like if you were to be floating on a planet somewhere in this globular cluster, you probably wouldn't experience a whole lot of nighttime. It'd be kind of unfortunate, I think.
You're absolutely right. Yeah, we don't know if planets can exist inside of globular clusters like this, primarily because the stars are so close together that those initial forming disks, we call them protoplanetary disks that orbit stars, are just kind of like loose sand, dust and gas. And gravity needs to take over and pull those things together in order for them to become stars and planets. And if planets are constantly being tugged at by neighboring stars that are so close to them, then those delicate protoplanetary disks might get pulled apart, and maybe planets can even form. So to my knowledge, I don't think we've actually yet detected whether or not there even are planets in these clusters, but they are very interesting because if you could live inside of one of these clusters, maybe you're an advanced civilization that has found out how to set up home inside one of them, then that means that the traveling to the next closest star or the next closest planet would be way easier because they're way closer to each other. Communication would be much easier. The closest star to us is like 4 light years away, but a star in this cluster might be light weeks or light days that you can make communication with.
Oh, that's cool.
All right, let's see how we're doing here.
Yeah, I also feel like it'd be very difficult to detect a exoplanet inside of this thing. It's just a giant. So I feel like not only is it massive, but it's also really bright. And so to see a an exoplanet in here, I feel like would be catching like a speck of dust on like a floodlight almost, you
Yeah,
know?
basically, yeah.
Yeah.
All right, this isn't doing as well. I'm going to switch back to our previous mode because the computer's having a little bit of issue stacking the image together. Sometimes if the computer can't make out objects in the picture, like stars and stuff like that, it's not able to align the image. And they might look really clear to us, but I'm wondering if it's because of all the extra moonlight that we have right now that it might be having a little bit of a harder time. So we'll try again.
Okay.
Now, what we've noticed is that in clusters like these, although they are very old, is that we'll sometimes see stars inside of them that look new. And you might ask, like, well, how could a new star form inside of a cluster that's so old? Although a star-forming material has been used up. But what can happen is that sometimes these stars will collide with each other. And when they do, it's almost like forming a new star. And we'll see a bright blue star come within the cluster. And we call those blue stragglers. So these are new stars that eventually have basically formed from colliding with each other. All the hydrogen gas in them gets all stirred up. And it basically will form a new star that we call a blue straggler.
That's interesting. I didn't actually know that.
Yeah, and it was kind of a mystery for a while because we're like, oh, wait a second, a lot of the stars in these clusters are old, like billions and billions of years old. And we'll see a lot of kind of red they're even seeing in the cluster now from those older stars. But then we had these bluer points of light inside of them, and people were wondering, like, okay, well, where did that come from? So it looks like it might be from the collision of some of these. Now, I'm having trouble kind of getting a lot of like that darker image around the cluster, and I'm thinking that's because some of the glow we're seeing around the outside might be from moonlight. And so I think that's part of what's going on here. Let's see if I can cut more of this back. There we go. The moon is a very jealous object, and it wants to be looked at. And we will get there. But on nights like this, it's putting off a lot of glow into space. What is, if we were here in person, what do clusters like this normally look like through the eyepiece?
I've heard them be described as like a dash of salt, kind of like
Yeah.
on a black table. I think that is such a cute description for them. I definitely have grown to appreciate what these clusters look like in person. Because when I was a little bit younger, I just wanted to look at the planets, and I thought they were the most fascinating things. But looking at these clusters, they're so, I don't know, sparkly and bright.
Yeah, every
They're
time
very pretty.
when I've looked at these, it kind of almost look like a collection of fireflies, even, which is pretty cool. So, um, and but yeah, it's one of my favorite things to look at through the telescope is looking up and being able to see like this star cluster through the telescope. So if you're up in person, and make sure that you always, if you have the chance, make sure to come and visit us in Starry Nights in person. We switched to doing virtual Starry Nights one day a month, mainly because it was requested by a lot of people who were able to visit us from abroad, or if they couldn't get all the way to Vancouver, they might be in other parts of the province or even the world. That's why we started doing these again, and they're actually a lot of fun. So, and sometimes we can show things that otherwise we wouldn't be able to show because they're just too faint to be able to see otherwise through the telescope. All right, what do we have? We can probably move on to the next thing. What's next on our list?
Hey Matthew, we got asked an interesting question in the chat, and I was wondering if maybe you had an answer to it.
Sure.
About fast radio bursts. I think it was regarding the topic of the star collisions within the globular cluster. And basically, the question was whether or not these star collisions are associated with fast radio bursts.
Oh, that's a really good question.
I'm not 100% sure, but I saw you looking at fast radio bursts. You were looking that up before the stream. I was wondering if maybe you had some words to say or maybe an answer. I'm not 100% sure.
Yeah, that's a really good question. Yeah, that's a great question. So fast radio bursts are still kind of a mystery. We don't know where they come from. Some of them are really short. Some of them are even shorter, like milliseconds of time. But they're like these intense bursts of energy. And sometimes in just like a second or a few milliseconds, they can give off as much energy as our sun does in a matter of days. Sometimes like 3 days worth of sun energy. So we actually don't know where those are from yet, but Interestingly enough, related to this question, some of the fast radio bursts that we have observed are from globular clusters. So it's possible they are from stellar collisions. They could be from things like the formations of black holes, or black holes consuming things, or maybe the collisions of like neutron stars, the dead cores of stars. But so far, we haven't actually identified what the source of fast radio bursts are. Some of the research on fast radio bursts, though, is being done in British Columbia. So we do have a radio observatory in BC called CHIME, and it is doing research on fast radio bursts because we've found these things, we've detected them, but we haven't quite figured out what they are yet. But that very well is a possibility.
Great. Thank you for answering that. I saw that and I thought that was a really interesting question, but I haven't brushed up on my space knowledge. I forgot what fast radio bursts were, but I think they're probably they are what they sound like.
Yeah, it's a fast
bursts.
burst of radio energy that no one knows what it is yet. No, you're absolutely right. There's another question here from Simon. Simon asks, how old do stars get before they go supernova? So that's a great question. It depends on the mass of the star. So stars that are more massive burn through their fuel counterintuitively more quickly. So even though it's made out of a little bit more mass, or a lot more mass and a lot more fuel, it's like it's burning the candle at both ends. So very massive stars will burn out in a few million years before going supernova. Other stars will burn out sort of medium mass stars like ours in a few billion years, and the lowest mass stars in trillions. Some of the smallest stars in the universe have never burned out, never since they formed at the beginning of time. The universe is not actually old enough for them to have ever fully burned out. But they don't necessarily go supernova. Only the most massive stars will blow up at the end of their lives. Less massive stars kind of have a slower death. And we'll actually see an example of one of those stars later. So we're going to get to that too.
Yes, I was going to ask you, like, we'll put a pin in that for now.
We'll put a pin in that for now. That's right.
I want to talk about that a little bit later when we're actually looking at those objects, for sure.
Okay, so this glowy thing in the sky that's taking up our sky, the moon, let's finally just take a look at it. It wants us to look at it, so let's go hop over toward the moon.
All right, sounds good. There's a lot of good stuff to talk about with the moon as well.
Oh, for sure, yeah. Yeah,
I was recently doing a project on quantum telescopes.
This is so cool. I'd never heard that word or those two words put together until you had mentioned them.
Yeah, it's very up and coming. It's a very new field, or an application of quantum mechanics and quantum internet. And one of the questions that I got asked when I was doing this presentation on quantum telescopes was like, how would we overcome like the atmospheric issues with imaging and whatnot. And I started talking about putting these quantum telescopes on the moon. And I don't know how realistic that would be, because I feel like it's already pretty difficult to send things out to the moon, and so to have to send a whole bunch of quantum repeaters and the internet over to the moon would be pretty difficult. But yeah, no, it's only something that I recently started studying up on, and it's super interesting. I think it could be the future of telescopes. Yeah, and it's a fun thing.
You were attempting to explain this to me, and I was like, wow, like I'm sure I don't even fully understand the concept, but basically, like, what you were saying is that with quantum telescopes, you're able to kind of improve upon a current method that's used in telescopes called interferometry, which basically will link telescopes together to make one like super telescope, but better. And I'm sure you can do a better job of explaining it than I can.
Well, no, it's pretty good. It's basically the gist of it. Like, you have certain optical telescope arrays, such as Chara in New Mexico. And what's interesting about Chara is that it's only 6 telescopes. It kind of forms like a Y shape. And each telescope has a mirror of diameter of 1 meter, which is actually comparable to the Trottier Observatory telescope. And I found that really fascinating because the Trottier Observatory telescope has a mirror of 70 diameters, 70 meters, 70 centimeters in diameter. And so they basically set all these 1 meter diameter telescopes up in such a configuration that they have the angular resolution power of a telescope that is, I believe, 330 meters in diameter, which is crazy. So, yeah, quantum telescopes basically can improve on that, because the farther away we make these telescopes from each other, the more difficult it is to basically keep the quality of the image. We sometimes, the photons, they're traveling through these vacuum tubes, and you might go through things like just photon loss in general, light loss, or just random phase fluctuations. And using quantum entanglement and teleportation, you can actually preserve a lot of the information and the state of that photon, or the state of the light, which greatly improves your imaging, basically. So it's really exciting. I don't even fully understand it. So when I'm explaining it, I feel like a little bit of an imposter, because I don't fully understand what's going on, but it's really exciting.
That sounds so cool. So like where's an example in that people could check out, or we could even maybe show it here, of where we have linked telescopes together to act as a super telescope before that's done something cool?
So yeah, as I mentioned before, we've had Chara. There's also the Very Large Array, which VLA, as it's called. And that is, I'm actually not sure where the Very Large Array is. But I don't know if we actually, do we have anything like that in BC? Like an array of telescopes in BC? Is CHIME kind of like that? I'm not 100% sure.
CHIME uses several. I don't know if they're using interferometry, but my understanding was that we were able to, even not like outside of the scale of one country, that across like the planet, we basically turned the world into one big telescope once, using interferometry to take an image.
Yes. So we have done that. I guess, are you alluding to the Event Horizons telescope, perhaps? Okay. Yeah. So we have done this before, using the Event Horizons telescope. That was kind of like a worldwide endeavor. Super cool. It was like a global project, and we needed to have telescopes across the world, because the wavelengths that we're measuring, they're just so long, across, basically. And so that's how we were able to get images of the black hole in our Milky Way. I don't know if that's the one you're looking at right now.
Yeah, I got pulled it up right here. Yeah.
Beautiful. Yes. So that was the thing about the Event Horizons telescope, and measuring things that are like frequencies, I guess, that are more relaxed, or like longer wavelengths, is that the telescopes can usually do their measurements locally. At least for the Very Large Array, they do radio wave measurements, and those telescopes don't actually really need to be connected. They can actually do their measurements locally, I believe. And so, yeah, but I don't know if they did their measurements for the Event Horizons telescope locally and then just sent all the data to each other, or I'm not sure how that worked. But yeah, that basically we turned the Earth into a giant telescope, and got some pretty cool results out of that. So
yeah, including this, one of the only 2 black hole images that we've been able to resolve so far. For those of you who've never seen this image before, this is the black hole at the center of our galaxy. It's called Sagittarius A star, and it's massive. It weighs about 4 million times the mass of our sun. The ring around the outside, the kind of glowing space donut that you see here, is all the stuff that the black hole is munching on. So planets and stars and dust and gas, it's all spiraling around. And the actual black hole is in the center. It doesn't give off energy because it literally swallows light with its gravity, but we are able to see the black hole's meal kind of spiraling around the outside, like water circling the drain. And one of the things that gets a giggle out of the students that come by our observatory is when we tell them that when you fall into a black hole, you get stretched out into one long strand of atoms in a process that's known as spaghettification. So, hey, Indra, what did the black hole say to the astronaut?
I don't know. What?
Why such a long face?
Oh, ha ha ha.
I know.
It's a good one.
Yeah, thanks. Anyway, so we used interferometry and the connection of telescopes to take this image of this black hole because as big as it is super, super far away. And so it's really tiny in the sky. So the resolution of the telescope, and here's something to think about because we could use our own moon behind in this image to kind of give an example. You're looking at the moon behind this image of the black hole. Right now, with our telescope, the smallest features that you can see on the moon in this picture are still about the size of a kilometer across. So even the tiniest speck that you can see in the moon back here is still 1 kilometer wide, which is about the size of Burnaby Mountain, to give you an idea. This black hole picture, in retrospect, is about the same level of resolution as me putting an orange on the surface of the moon and you being able to see that orange. So that gives you an idea of just how powerful that Event Horizon Telescope was. And that's using the technology that Indira was talking about, the interferometry and connecting things together. But if we could actually go to the moon and use one of those craters maybe on the moon and build something similarly, who knows what we can build up there. We're also thinking of putting radio telescopes on the far side of the moon in particular. So one of those projects is called the Far Side mission. Did you want to chat about that at all? The Far Side telescope?
Yeah, so there's like two there's two ideas, I guess, with the Far Side telescope. There's Lucy, which I believe is just like a rover or robot that would be deploying smaller, basically like little robots that could do these measurements. I haven't really learned too much about that. Instead, I'm more interested in the Lunar Crater Radio Telescope. So that one involves basically making one of the moon's craters a telescope dish. Basically,
That's so cool. That's so cool.
Yeah, it's really cool. And so I'm not sure. I think they're planning on putting that one out, if I remember correctly. I think in like the 2030s. I don't know. Do you know?
I don't know if there's like a hard plan for it yet. That's a good question, but it is really neat because basically the Earth is so noisy. Our planet gives off so many radio signals, and the moon can act as a natural shield for those radio signals. So if you have a telescope dish on the far side of the moon, it gives you this nice and like quiet view or listen of the radio signals from deep space, including things like maybe signals from aliens, one of those things, but also even studying the cosmic background radiation, that like faint glow of the Big Bang that's left over from the beginning of time.
Yes, we'll be able to listen to the universe's secrets on the quiet far side of the moon.
I know, I'm so excited. So exciting, so many secrets. I've sort of just been kind of scanning the moon surface. If you're wondering why it's sort of wobbling around all over the place, I'm just like, I've got, I don't know if you can see it in the view I've got right here, but this is the telescope control interface. And literally I just have like arrow keys here, and I'm using them to just move around in different places of the moon's surface. But one of the other cool things about the moon, so I just want to talk about this quickly, is that we're going back. So we are going back to the moon next year, which is super wild. You probably can't tell from where you are, but if you've ever met any of us, none of us are old enough to have been around for the last moon landing, which happened over 50 years ago now. But we're going back to the moon next year in a mission called Artemis 2. So the last one that went to the moon was called Apollo. Some of you may have been around for that one. And we haven't been back to the moon since 1972. That was the last time that anyone was out there. And this is the crew that is going back. So these are the 4 individuals that are going to be part of that mission. The reason why it's called Artemis 2 is because Artemis 1 already launched. It was a test of the new spacecraft called Orion, and so they sent it out toward the moon and back just to make sure that it was actually working properly. I went down to go see Artemis 1 launch, and I missed it because when I went the first time, it was during the summer when Hurricane Ian showed up in Florida, and they literally had to like move the thing back into the space garage because they were like, it's going to get blown over by all the wind and stuff.
That's right. I remember that. And I was thinking about how unlucky you were and how unlucky it was that we didn't get to have the launch that day.
I know. So it ended up going in November of 2022. And then in November of 2024 is when this batch of astronauts will be heading up. So I was going to go through their bios and stuff, but just needless to say, they all have like 14 degrees They are very well-educated people. Christina Koch is super cool. She's got her Bachelor of Science in Physics, Master of Science in Electrical Engineering. She started as an engineer at NASA in the lab for high-energy astrophysics, but she worked at the Antarctic for like 3 years, and she lived there once, like over the winter in Antarctica. And the reason why this is cool is because there's sort of a parallel to this in that the part of the moon that we're going back to for these new missions is the south pole of the moon. And the reason why we're going there is because we have found craters near the south pole of the moon that are so dark because of the angle that the sunlight shines near the south pole that they never experience any sunlight. They're called permanently shadowed areas, and we have found water. Well, ice water in particular at these poles of the moon. And so we want to go there toward the South Pole because that water could be used as a base. It could be used for rocket fuel. You can separate hydrogen or water to hydrogen and oxygen for fuel. And so that's exciting that we're sending these astronauts out. They're going to be circling the moon and coming back. And then in 2025, we're hoping of doing Artemis 3, which will actually land astronauts on the surface of the moon. And to bring back that picture of these astronauts again, it's a much more diverse group of people this time. It's not just like white American dudes. We actually have like a more representative group of humanity, and there's 15 countries going this time instead of just one. And one of them this time around is Jeremy Hansen, who is a Canadian. And of course he was selected because, you know, he's an F-18 pilot. He has his master's in physics, but I think Jeremy Hansen was also selected to go because he looks like a real life version of Buzz Lightyear. Tell me that isn't a Buzz Lightyear face. That's like if you took Buzz Lightyear and turned it into a human, that's who it would be. So there you go.
You know, that's a very good observation, Matthew.
Thank you.
I think you might be onto something.
Yeah, that's why. A very strong chin, that cleft chin, that means you could go to space. That's why. It's one of the things that you need.
Yeah.
All right. What else are we doing? What's next?
I don't
more
know,
planets?
actually.
Are we doing more planets, I think?
Did we have Jupiter?
I think we had Jupiter on the list, so let's do that.
Okay. Jupiter on the horizon. Yes.
Literally on the horizon.
Literally.
Someone had pointed out that Jupiter and the moon are quite close to each other in the sky right now, so if you're outside, you may have noticed that. Jupiter being the brightest object in the sky next to the moon right now. And I think actually some of our team of spacey humans is actually on site right now. I haven't seen them in the video feed from outside, but apparently some people are actually out there. I think Dr. Joanna Wu is there, and some members of RASC are there as well. Oh, by the way, I forgot to mention we have our besides the team on site, and then of course Indra and I on the stream, we also have Kieran and Zach from the Trottier Observatory team are on right now, and Michael from RASC, the Royal Astronomical Society, is here moderating. So you might have seen them posting in the moderation feed as well. So shout out to them for being here today too.
Yes.
All right, let's see. Ta-da!
Very cool. Last time Starry Nights happened, which I believe was last week, I got to see, what was it? There was a moon that was like eclipsing Jupiter. Like it was like
nice.
passing in front of Jupiter. Yeah, so it's so cool to see that. Just because you can kind of see like a bit of like a shadow, or like you'll see just like this white splotch over top of all the bands across Jupiter. And so I'm very fortunate because I was able to see that twice now, and it's so cool. It never gets old. Yeah, it's really interesting. I forget whose telescope it was that I saw it on. Otherwise, I'm drawing a blank. Otherwise, I'd give them a shout out right now because it was such a cool opportunity. But yeah,
there was there to help identify the moons of Jupiter. So around, you can see Jupiter here, and you can see actually the cloud bands of Jupiter showing up really clearly today. So that's cool. And then you can also see there's these dots around Jupiter here. So those are Jupiter's 4 largest moons. I can't make out the 4th one right now. It could be behind, or sometimes it's in front. So it's kind of, I'll pull up the brightness here a little bit. I can see a bit clearer. But there used to be a Twitter app called, or one of the a Twitter account called Jupiter Moon Position, and it just like, it would tweet out using characters what where it would be like J, and then it would have the letters of the different moons beside it. So if you were looking at it, you knew which moon was which. And unfortunately, that account is not posting anymore, because it was a really handy way to look at the moons. Because sometimes, especially with a mirrored telescope, and you forget how many mirrors is flipping around your image by the time you see it, you forget like where it is that you're looking. Now, one of the things though, if you look really closely right now, it's hard to make out. But if I zoom in here, let's zoom in. Is this going to be too fuzzy? Oh, that's going to make it worse, I think. But it's hard to make out. But right in the middle where my mouse is, right there, you might notice that there's a tiny little dark patch. And that dark patch is a shadow from one of Jupiter's moons. So even right now, one of Jupiter's moons is casting a shadow on Jupiter. And I don't know which one it is right now. If anyone knows in the chat.
Joanna has put in the chat, Ganymede. I don't know how to say
Ganymede
it.
shadow. Okay, thank you. Yes. So
Ganymede. She says it's the dark spot in the upper right.
Right. Oh, up here. Yeah, that might be that one over there. There seems to be one toward the center, and that is probably one of the shadows of the moon as well. I couldn't tell you which one it is in the moment. This is why some of the apps are really good for this, because it'll tell you like which occlusions are happening by which moons at that moment. But yeah, looking up right now, you're seeing some of these shadows in there from some of those moons going around. By the way, Jupiter's moons, they're referred to as the Galilean moons. There are many more than 4. Like Jupiter has almost 100 moons, but these are the ones that are most easily visible from the telescope. And they are so called because they were seen by Galileo. And Galileo noted that they like moved around, and so they would circle Jupiter, and that was some of the evidence that smaller, less massive objects orbited larger, more massive objects, which put more evidence that we were not, we were not at the center of the solar system, but rather that we were orbiting around the sun. And I believe you can look here. You might see a reddish spot, and that is the Great Red Spot on Jupiter. So that is it right there, the big storm on Jupiter, that hurricane that's twice the size of planet Earth. Oh, there you go. Yeah, we just got that question. So there, question from a 5-year-old. What is the red spot on Jupiter? And another question from an 8-year-old. Any atmosphere on Jupiter? So yeah, that red spot on Jupiter is the Great Red Spot, or the storm. And the reason why that storm is happening is that Jupiter doesn't have just some atmosphere. Jupiter is all atmosphere. Jupiter is just one giant ball of cloud in outer space. And just like clouds on Earth, those clouds can have storms. And Jupiter has the largest storm in the entire solar system. It could swallow the Earth more than 2 times. So Jupiter has crazy fast winds, and it's the fastest rotating planet in the solar system, and that rotation and the winds create those amazing bands and clouds around Jupiter that you can see here. Yeah, you can see the red spot. Yeah. There it is right there. Yeah, I'm not crazy.
Yeah. Yes. Nice. No, I think the day on Jupiter is like 10 hours, 10 Earth hours.
Yeah, I think that's right. Short. Yeah, it is very short.
But yeah, I wanted to go back about the moons, because I think you mentioned it has like 100 moons, maybe.
I think we're close to that. We keep finding more all the time. A lot of them are very tiny.
Yeah, and so I was reading up on what they have on the NASA site, because I had someone at the H.R. McMillan Space Center ask me how many moons Jupiter has, or how many moons the solar system has, and I wasn't sure. So after I checked up on NASA, and it turns out that there's a lot of things orbiting Jupiter, and there's a large gray area between what is defined as a moon and what is defined as just like a space rock orbiting Jupiter, basically. And so if they were to count all of the objects that were orbiting around Jupiter as moons, they would have like, I want to say 500 to like 700 objects.
Goodness. Do you think there's going to be some trauma similar to like moon demotion, like there was for planet demotion when Pluto happened? Do you think it's going to happen?
Oh man, I don't know. I feel like Jupiter has so many. Like
no one will notice.
Yeah, no one will notice.
It's even more tragic, maybe. I was a moon for a while. No one even knew. No one even knew I was demoted.
Yeah, no, I find it so fascinating. Like, Marley from the HR Mac, she's the astronomer there, and she told me that people, like humans, like to put things in boxes in terms of like organization, and space doesn't really care. Space just does what it wants.
It's just there.
So we're trying to like categorize what these things are, like what is a moon and what isn't, and space doesn't care. It's just like, all right, Jupiter's gonna have another moon. Here we go. Like,
yeah, I'm still spinning around. It doesn't matter what you think. Yeah.
Yeah.
Jupiter likely the first planet to form in our solar system, and probably shepherded a lot of the other material around the solar system with its gravity, just because it's so massive. In simulations of how the solar system may have formed, it looks like Jupiter actually at one point started careening toward the sun. And it might have taken out all the material in the inner solar system that formed Mars, Venus, Mercury, and Earth. It looks like Venus, or rather that Jupiter at some point may have been as close to the sun as Mars is now. And it looks like Saturn forming outside of Jupiter pulled Jupiter back out. And Jupiter and Saturn have this 2-to-1 orbital resonance. For every time Jupiter orbits once, Saturn orbits twice, and they kind of stabilize each other and then therefore the rest of the solar system. So it might be that if a big planet like Jupiter forms and another gas giant like Saturn doesn't, that planet just like careens toward the sun. And maybe that's some of the hot Jupiters that we find, these gas giant planets that are really close to their stars. Maybe those solar systems aren't habitable. Maybe it doesn't form the rocky planets in the same way. So Jupiter might have been a scary thing. It also looks like Jupiter, though, might sometimes act to protect the planet by blocking us from comets and asteroids. At some points in history and other times of history might have actually thrown the rocks and asteroids we needed our way that were carrying the water that formed the ocean. So all these things had to happen in order for us to be here having this conversation right now, which is pretty wild.
Yeah, it's just a bunch of stuff happened, and now we're here.
And now we're here. A bunch of stuff happened, and now we're having starry nights. It's pretty wild.
Yes, yes. Yeah, actually, I was reading up on like the sun's whether it has like a little bit of an orbit, like if it has like a wobble.
Okay.
Because the way that we look for exoplanets around other stars is by looking at the star's radial velocity, right? You want to see if it has like a little bit of a wobble, and if it does, then that means that there's probably like a planet orbiting around it, and both objects are kind of orbiting around like a common, like I guess common center of mass. And it turns out that Jupiter is probably the only reason why our sun moves back and forth. And Jupiter is so heavy that it doesn't actually, like, our sun doesn't have like a completely circular orbit. It's kind of like an opened orbit, like it's going all over the place basically. And so if anyone were to look at our star, they would be able to detect that there is in fact a planet around our star, and they would probably look at Jupiter and say, oh, look, there's an exoplanet around that star. And I find that really fascinating.
Cool. Yeah, just from the wobble of a star. And likely, I'm guessing Jupiter causing the most wobble to our own star that way, right? So
yes.
Yeah.
Yes.
All right. I'm going to move on to the next object. Now, sometimes one of the bugs that happens when we are remotely connecting to the observatory computer is that keyboard input commands stop working properly. And it's like as if you're holding the shift key or the control key. So rather than getting characters, you get random stuff. And I'm worried that might have just happened. So let's try. We're trying to get to the dumbbell nebula. So M27. Is it going to let me do this?
A little bit more troubleshooting, I guess.
Yeah.
Well, the dumbbell nebula is very interesting, very cool. I know it's a popular target for a lot of amateur astronomers, including myself. I tried to look at it from my own telescope, and to this day, I don't know if I really saw it or not. I don't know if like there was a cloud that passed by, or if I just like was looking at the spot long enough to convince myself like that I was seeing the nebula, but it was very faint from where I was. My usual viewing spot is like the end of Harris Road in Pitt Meadows, just because it's easy to get to. But yeah, I was reading up that it's got like a magnitude of like 7.5 or something, which is, I'd say it's pretty bright for a nebula, but I don't know. Matthew, what do you think?
Yeah, absolutely. Yeah, it is one of the brighter nebulae to be able to see in the sky. And I want to be able to show it to everybody. What if I do copy and paste for my computer? Won't let me do that. Uh-oh.
Oh, so we have a question that I will just answer while you're continuing your troubleshooting.
Yeah, thanks.
Um, Anna Sonia. Oh, I know you. Hi. She's asking if Jupiter protects us from stuff with its gravitational pull. Yeah, I would say like yes, but also sometimes perhaps no. I've heard some stories that apparently, Jupiter's got this massive, gravitational pull, and so it'll protect us against meteorites. It'll kind of take the hits for us. But then I've also heard people say that they think that Jupiter also might be hurling meteorites at us, but we haven't been hit by anything. So I think I would argue that it's doing its job and it's protecting us basically from being hit by any sort of large meteorite or anything like that. Yeah, that's a good question.
Hmm. Yeah. Okay. So, bit of an issue here because the computer is no longer allowing us to send typing commands to the system. This is one of the disadvantages of maybe doing this remotely. All right, just 1 second here.
Is there a way we can do like find an object without having to search?
Well, I might be able to copy paste, but it won't even let me right click. Ah, here we go. Okay, can I do this? Will it let you do this? Aha! Okay, no.
Oh, okay.
So if I highlight this whole thing like this, it looks like I can copy from my own computer, but paste this computer. So even though we can't use the keyboard, that might still work.
I was gonna say if we can't type, we could always just try to find it ourselves. We
Yeah,
are
this guy, like the old school way.
yeah.
All the experienced Rask folk are on there being like, you should be able to do this without the computer. Don't use it as a crutch. Okay, here we go. I think we're moving. Hooray! Problem solved.
Beautiful. Now we can talk about the nebula.
So because the nebula is faint, we're going to go back to stack mode again rather than live feed like we were doing with the planets and the moon. So we'll clear the previous stack when we were doing the star cluster.
Oh, we got asked another really good question. I don't
Okay.
know how well I can answer this. But someone's asking, how do we know the mass of Jupiter? We can't really put it on a weighing scale. That is very true. I know how we measure the masses of like other stars and whatnot, but in terms of Jupiter within our own solar system, do you know why or how we can weigh Jupiter?
Yeah, so we can actually, we're able to calculate the density of objects in space because we know more or less what the objects are made of. And Jupiter is primarily made of hydrogen and helium. It's kind of big ball leftover material. And then we know how big it is. So giving it its radius and the material that it's made of, we can get an estimate of its density. And if we know the estimate of its density, we can also calculate how high its gravity is, just made based on the material that it's made of. So that's how we're able to do calculations of the mass of an object like that. We can also see how much it's changing the direction of objects around it. So if you know that there are other bits of rock and ice and dust that are orbiting something, and you can see how curvature, or with the curvature of those orbits, then you're also able to track the motion of those things as well. Just like Dr. Wu is saying here. So just by the motion of the object through space is one of the other ways you can figure that out too.
Oh, she's done that too.
She's done that project once, so there you go. We have an expert in our midst. All right, let's see.
I guess it would be similar. I knew that for stars it was the same thing. I just wasn't sure about how you'd go about it with
For sure.
Jupiter, but I guess
Yeah,
you could just do those calculations, right?
totally. Yeah, just like so another example of that is how we figured out the mass of the black hole at the center of the galaxy. So the black hole at the center of the galaxy exerts a gravitational force on stars that are orbiting the center of the galaxy, and we could figure out what the mass of those stars is because we can see them and we see the orbit that they're taking, and that allows us to figure out the mass of the black hole. And we know the black hole at the center of the galaxy therefore weighs about 4 million times the mass of the sun. I believe it's Dr. Andrea Ghez that made that calculation. She had observed the motion of stars at the center of the galaxy for like almost, I think, over 15 years, watching all those stars move around.
Yeah, and fun fact, I totally forgot to mention this about Saturn, but Saturn, even though it's like a very, very, very large planet, it's actually not that dense at all. The gravitational pull on Saturn is just a little bit more than it is here on Earth. I think if you were to weigh like 60 kilograms on Earth, then you would weigh about like 68 maybe on Saturn. So that's why they say, like, if you could put Saturn in like a bathtub, let's say, it would float because it's not that dense. There's not a whole lot of material, I guess, or just not a whole lot of heavy stuff inside of Saturn, despite its size.
Cool.
Very interesting.
Look, it's the Dumbbell Nebula. We found it.
Oh, we found it. Let's go.
Yeah, so we're and the computer is locked onto it. So that means that unlike the globular cluster earlier that we're having issues layering the data, this stack is happening. So this image is stacking correctly, and so we are getting more and more data. So even as we're sitting here staring at it, will get clearer and clearer and clearer. So what do we know about the Dumbbell Nebula?
I know that I have a little bit of beef with its categorization of it being a nebula. Because it's a it's a planetary type nebula, and the name is very misleading, which is why I have an issue with it, because I thought that meant that it had to do with planets in some way, shape, or form, but that's not actually true. The Dumbbell Nebula is a planetary nebula, and I think it was one of the first to be one of the first planetary nebula to be discovered, I believe. But basically, the person who was observing this nebula, way back in the day, probably couldn't see the object as well or as clear, and so they thought that it was a planet, basically. And so the name just kind of stuck. We later discovered that it was a nebula, but they just decided to basically stick with the name planetary nebula. So I've got a little bit of an issue with that, just because it's very misleading. But it's still beautiful, it's very nice. All the planetary nebulae are always like gorgeous, and I think we have another one on the list tonight that we might get to, right?
I think so, yeah. I think it was, if I'm right, I think it was William Herschel that described these as looking like planets.
Yes.
But in his defense, he did go on to discover Neptune, and that's not so bad, I guess, to put it, as a feather in your cap for astronomy, even though he led all of us astray with this misnomer. What's interesting is that we never changed it. We don't, we just keep calling them that, even though that's not what they are. These aren't planets. Now we know that they're huge. In fact, this nebula is enormous. It's way bigger than a planet, much larger than even a solar system.
Yeah, I personally don't have any beef with William Herschel, I'd say.
He'd be glad to hear that.
It's more like, why did we keep the name? Like, why did we keep it in the name,
Right.
But yeah, sure, that's good. I didn't know that he had discovered Neptune. It's very interesting.
Yeah.
He's a planet guy.
He's a planet guy. This thing is basically a dead star. So we're looking, Indra and I were talking about analogies earlier for how stars die. This is the death of a low mass star, so kind of like the size of our sun, maybe just slightly larger, but not much more than that. Larger stars will die as supernovas, so they explode. So this isn't a supernova. This is more like the gradual, slow expansion of a star near the end of its life. It's kind of like the analogy we thought of is when you're roasting a marshmallow, and it kind of just swells up into a bunch of goo and then sort of melts off into space. And that's essentially what's happening. And this will happen to our sun in about 5 billion years, which is a long time from now. But when you're doing talks like this with young people, and I don't know if this has ever happened to you, sometimes the fact that the length of time is irrelevant. It's just that sense of endedness, finality, that sometimes we've done, I've done groups of young people, and they get really upset. Now here's an interesting story. I was sitting outside one of the shows that we're doing at the Space Center, and it was actually my lunch break, and this young person comes flying out of the theater, inconsolable, just crying and crying. And I think what I perceived to be is this young person's grandmother was with them, and I think his name was Jimmy or something like that. And she's like, Jimmy, we talked about this, it's okay that the sun's gonna die, you're not gonna be around in 5 billion years. It's a really long time from now. But then he had this argument, and this was his answer. He's like, yeah, but I learned that some people believe in reincarnation, which means they keep coming back to the earth. But how can I be reincarnated over and over and over if there's no earth because it's been eaten by the sun? And I was like, yo, for real, I don't know how I'd answer that question. And you can see she just had this look of desperation on her face, and I was like, I'm not jumping in on this one. I'm gonna let that one be.
Oh my goodness.
Yeah.
What a very bright young man.
Yeah. Yeah.
I always find this so interesting. I feel like kids just have like a lot of strong connections with space. Like you'll mention, Pluto and how it's no longer a planet, and like, they kids they pick sides, and they will fight over their side, and
Yep.
I just find it so interesting. They get very emotionally invested in space. It's nice. I'd say that I was probably similar as a kid, so it's nice that it's still a thing.
I think it's so cool that they just think about stuff this way. Like they just have these profound, like Carl Sagan talked about this too. He said that children have these just profound questions and thoughts about the universe. And that his worry was that as we grow older, we become incurious, he said. So, definitely we don't want to send young people into existential crisis over the sun dying, but I think it's cool that we do think about these kinds of things. The center of this nebula is called a white dwarf. You can actually see it here in the picture. So that in the very center is the dead core of a star that had died. Probably we think this nebula is about 10,000 years old, and it's expanding at a speed of 31 kilometers per second. So it is now very large, about a light year wide. But that center white dwarf is one of the largest ones we've ever seen. It's only 5% the radius of the sun, but it has the mass of almost half the sun. It's basically one big giant diamond in space, a hot ember left over after a fire has died out. So no longer creating a flame, no new energy, it's just very hot. And ironically, or maybe counterintuitively, people think, well, space is cold, so things like this are going to cool down really fast. But space doesn't really have temperature. It's vacuum. And so when things are hot in space, it's actually really hard to cool them off. Because on Earth, when something's hot, you want to add something to blow like air on it or pour water on it or something to cool it down. But in space, it's really hard to cool things down. All they can do is slowly radiate energy off into space. And so things like this will stay hot for trillions of years, probably. Even when we launched the James Webb Space Telescope recently into space, before it could operate, we had to let it cool down in space for weeks. It took it to cool down just from the heat that it absorbed from Earth before getting into space. So these embers of stars will last for a very, very, very long time.
Yes. I I usually tell people that space has like an average temperature. But I guess explaining that it's more like it's like how you can't even like how there's not really sound in space, right? Because there's nothing for that temperature to or sound to propagate through. So I guess it would be kind of similar where there's nothing to for that temperature to propagate through and disperse it. You know what I mean?
You are right in a sense though, because the ambient radiant energy, background energy in space is only slightly above Kelvin. I think it's 2 or 3 degrees Kelvin or something like that. But
yes.
but that it's not enough to convect the heat off of something. It's not going to actually cool it down. So in these movies when people take their helmet off in space and they freeze instantly or anything like that, that doesn't actually happen. It would on Mars, but it's not going to happen out in outer space. All right, should we move on?
Well, okay. Yeah, I mean, it looks really nice. I also wanted to talk a little bit about the gas colors, but
oh, please, no, go ahead. Yes, yeah, go ahead. Yeah, go ahead.
Oh, okay, yeah. So, I was actually going to ask you the question, what do you think the gas colors are?
I'm going to take a guess. So I think the red I know is hydrogen on the outside. I think that's expended hydrogen gas, radiating out toward the outside. The inner bluish greenish colors, I'm going to say the oxygen. Is that what those are? I don't know.
Yeah.
Is it?
Yeah.
Okay, cool.
Yeah, so the red glow is from hydrogen and the blue green is from oxygen. It's being ionized, which allows it to basically glow a little bit. Ionization is basically when you're taking electrons off, or generally it's off, I guess, with the gases, and I believe it's creating that glow look basically. But yeah, I just wanted to mention that because it's really cool, so we could tell what the inside, what the star was producing. Or we could tell kind of what what was inside of the star, I guess. I don't know. What do you think, Matthew?
Yeah, no, and that's cool because what we found or what we discovered by being able to, it's neat that first of all we can figure out the ingredient list of something just by its color, which I think is super cool. That helps us to understand what space is even made of. And I believe it was Cecilia Payne-Gaposchkin. She was the one who figured out that most of space is made of hydrogen, and we found that out from the colors of things we see in stars. But that also means that stars are cooking up all these heavier elements that we're made of. So this is where we came from, and we find that out by looking at space and these stars and their colors. Is that we know that the atoms in our bodies were also cooked up inside of stars, like the oxygen coming out of this dumbbell nebula.
Yeah. It's very interesting to think about. Once again, a whole bunch of stuff happened, and now we're here.
And now we're here. A whole bunch of stuff happened. Now we're here having starry nights. Pretty wild.
Yeah.
Cool.
Star stuff, looking at star stuff.
Star stuff, looking at star stuff. All this time later. All right, let's see. Is my keyboard working again? No. Okay, we're going to copy and paste from my own computer locally. That's what we're going to do. So, copy.
What do we think about next?
And I think we're going to try a galaxy next. So we're going to try Bode's galaxy. The problem is that with these galaxies are sometimes hard to get even in good sky conditions, and with the moon being up, this might be tough to do, but we'll try. This galaxy is located also near or above in the sky one of the brighter buildings on campus, which also sometimes make this a little bit difficult. But it's so pretty, that's the thing, and so maybe we can try to get it. So if you notice, I'm spinning the sky around here. You can see the constellations on the sky, and the constellation that this galaxy is near is Ursa Major. So just off the bucket of the Big Dipper. So there's the handle of the Dipper and the bucket, and the galaxy we're looking for is right there. So that's where we're headed to. And this is one of those funny times where the telescope goes one way and the dome goes the other way, and they kind of meet each other on the other side.
Okay, well, bye Dumbbell Nebula. It was so pretty. I've never seen it look like that before.
It's so good, yeah.
I don't think I've seen it like through LiveStack before, so that was very nice to look at.
Yeah, and it even gets the colors are pop even a little bit more on nights when it's not quite so bright with the moon up in the sky.
Yeah.
All right, I think we're still staring into the dome. So let's see. Let's clear that. Okay, we're good now. So let's see what the next stack looks like. But if it's all glowy, like that first one was, we might be getting too much light pollution in that direction for it to work.
Is that towards the AQ?
Yes, yeah.
Yeah.
Oh, that's actually pretty good. You can see it
Not
almost
bad.
right there. Yeah, I can see the core of it anyway. Let's see what a couple more stacks does. And then if we can't get it super well, we can cheat. It's not quite cheating because we do have a processed version of this galaxy that is from our own telescope. So we can show that picture if this doesn't turn out super well. And that image was taken with data taken from our primary telescope, and primary camera. So we actually have an astrophotography camera that's created or that's used for really precise astrophotography, very colorful, very bright, very crisp. Whereas the one that we're using right now is mainly just for kind of what we're doing right now. Is more of like a live feed, just a quick stack, kind of see the color, a little bit of structure, but not usually collecting as much data as we do with some of our longer stacks in astrophotography, where we might be looking at the same object for like hours and hours and hours and hours and hours. All right, let's see. Well, we are stacking, so that's pretty good. Let's see what we can get out of here.
I wanted to talk about this galaxy with regards to galaxy evolution.
Yeah.
I'm a little bit nervous now that I know Joanna's watching, though.
I know. Good thing you're doing it. I don't want to.
Oh gosh. Yeah, I thought I'd share a fun fact, I guess. Hopefully I always get it backwards because this fact is very counterintuitive to me. But it's that spiral galaxies tend to be, looking at my notes, I already forgot. Spiral galaxies tend to be younger than elliptical galaxies, I believe. And it's kind of counterintuitive because you would think that like elliptical galaxies are like, just just forming and figuring themselves out and whatnot. That's actually not the case. They are the older ones. Um, and yeah, I did learn that actually taking Joanna's one of Joanna's classes. So hopefully I got that all correct. But yeah, so spiral galaxies are tend to be younger. Elliptical galaxies, which kind of look like eggs to me, they tend to be a little bit older.
So you notice that one of the other things that we're doing is when we get all the data from the telescope, where my mouse is right here, this is called a histogram. It's basically like all the red, green, and blue coming through the telescope, and then we can adjust the colors so that they balance properly, because they should all sort of fit along the same curve. Otherwise, you're going to notice the image is going to look a little bit too much red or a little bit too blue. We are hoping, though, while we can see the center core of the galaxy here, we're hoping that we would see the kind of spiral structure around the outside. And I think it might be just a little bit too washed out tonight to be able to see. This galaxy is actually really cool. It's about 12 million light years away. It's 96,000 light years in radius, so smaller than the Milky Way, which is anywhere between 100 to 150,000. But fast radio bursts. We were talking about them earlier. There is a fast radio burst that was detected in a globular cluster, like the Hercules cluster we were looking at in our own galaxy, from this galaxy. So this galaxy has one of those fast radio bursts from an orbiting globular cluster, and it interacts with another galaxy called M82, neighboring galaxy, where there's like these filaments of material that are kind of streaming between one and the other. And I don't think we're going to get much structure out of this one, unfortunately. But what I'll do is I'll show you the picture that we have of it, because it is a really good photo. That's not it. There we go. Slideshows. These are some of the images that we will show as well to visitors when they are coming in. When we don't have a lot to see during the day. I thought we have a better one than this one. That is not that great. I swear we have a better M81 somewhere. Joanna, if you're still in the feed, where's the better M81 galaxy picture? Because I know it's in here somewhere. No? I thought it was in that folder. Oh, I should have checked that ahead of time.
I feel like that one picture might be the only one that we have.
Oh, we have a good one. I know we do, because I was trying to image that galaxy, and when I found out someone already had and it was really good, I was like, no. But yeah, there was a good ME. Maybe it's is it on the desktop somewhere? I won't belabor this too long, but I know we have a good ME1 picture somewhere. Is it in gallery? Others? Aha! I found it. There it is. This is it. So.
Oh, I shouldn't have doubted you. Look at that.
Look
wow.
at that. I know, it's so pretty. It's one of my favorite galaxies. It is very, very beautiful. And so if we had a chance to sit down and stare at this image or this part of the sky with clearer skies and our higher power camera and with hours and hours of time, that is what we'd be able to pull out of it. So the only thing that we're seeing really in the image right now is that little blob in the center, which is the core of the galaxy. Galaxies tend to form from the inside out, so all the older stars tend to reside toward the middle, and as stars age, they get that oranger and redder in color, and so that is why we're going to see sort of that color in the core. The outside of the galaxy is made of younger stars. The brightest of them tend to be blue, and these magenta regions along the arms are where stars are being born. So those are star forming regions. And oh, that was one of the other things I was going to mention before we got started, is that we're kind of between the seasons right now of being able to see star forming regions in our own galaxy, because in the summertime there's a lot of really cool colorful star forming nebula that we're able to see. The next one that's coming up is a little bit more toward the winter, when we can start to see the Orion Nebula. It has these amazing colors, but we're kind of between seasons right now, which is why we're between seasons. The moon is up, and so we've got some of those challenges in looking for those more colorful nebula today in space. Should we try another galaxy, or should we just abort galaxies and try something different?
Can we try the Pinwheel Galaxy?
You want to try Pinwheel? Let's do it.
We're talking about nebulae. We're talking about galaxies. Let's combine it and
let's combine it.
Yeah. Although I don't know if we're able to still see that supernova that went off. I don't know if that's dim.
It will be. Yeah, I think that one's faded out, but we do have a picture of it, so we can always pull that one up. So we do have an image of that too.
Beautiful. Okay.
Okay, so this galaxy is close in the sky to the other one. So we are looking here off the bucket of the Big Dipper. So now we're going to be over here more toward the handle. And this is known as Messier 101 or NGC 5457, sometimes known as the Pinwheel Galaxy. It was actually the first thing that we imaged, completed color photo with the telescope back in like 2015 when the observatory first opened.
We've got a couple questions here.
Sure. Let's do it.
I don't know. Oh, maybe Karen's answering them.
Okay, cool.
But do you know who took the picture of the the Bode's galaxy?
I don't. I don't think that one. There isn't a name attached to that one. Normally we will mention who is doing them, but I don't know who did that one. So if anyone knows at the observatory who processed this one, they did a really good job. So please let us know because it's really well done. That's an awesome one. I didn't do that one, so I can't take credit for it. That's not one of mine. So yeah, whoever processed that one did a really good job. Okay.
Oh, there's also another question asking how much older are the elliptical galaxies than spiral? That would be a great question for Joanna. I don't. She does this stuff for a living. I'm assuming that it's a long time. Generally, things in space, it takes a long time. So I'm assuming that like spirals are.
I think it also has to do with the amount of available material, like star forming material in each of those galaxies. They might have different lifespans. I would think kind of like stars. It might be similar to that, but I don't actually know. That is a good Dr. Joanna Wu question. So Dr. Joanna Wu, if you could tell us relatively, if you look at an elliptical galaxy, can you tell how much older it is or how much farther along in its lifetime it would be than a spiral galaxy? Dr. Joanna Wu actually runs a workshop on galaxy structures at the observatory when we have like schools come in and visit. I am sorry, Indra, I don't think we're going to get anything from Pinwheel. I'm not seeing anything in this direction in the sky. We're not even getting stars up here. That possibly, I wonder if we're actually starting to get cloud cover now. So what I'm going to do, we have a camera that looks up in the sky and checks for clouds. Let's see how that is doing. It might be frozen. Because that image looks like from earlier in the day.
Yeah. I don't think it's that bright anymore.
It may not be. Okay, that's fine. Yeah, but it looks like it just look like glare and glow in this part of the sky. It doesn't look like anything. Oh, Dr. Joanna Wu said she is in and out. Just heard her name. Okay, so what we were asking Dr. Joanna Wu, because there was a really good question about how are you able to tell how much older an elliptical galaxy is than a spiral galaxy? Since Indra was mentioning that elliptical galaxies are older than spiral galaxies, so can you tell? Color is a rough way to tell the galaxy's age. So I'm guessing by the combined age of the stars in that galaxy. So Alexander Hallett's question. Thank you. Awesome. All right, so I don't think this is going to work out.
Wait, so did I get it right the first time?
Oh, you did? Yeah, you totally got it right. Yeah.
Okay.
Yeah, I know that we debated that one earlier before we got on, but you were totally right. Yeah, that elliptical is younger, or sorry, spiral younger, elliptical older, but it was just being able to see, could you actually tell by the structure how much older it is? But Dr. Joanna Wu saying that it's also by the color, so I'm guessing how much redder. Yes, red means old, blue means young, based on the stars. Cool. All right.
Ooh, okay.
What else we got here? Let's see. We could try. There's an open cluster here we might be able to try out. So let's try this one.
Oh, is that the
Hades cluster?
Hades?
Yeah. So this is an open cluster. It's one of the nearest to us. Open clusters are clusters of very young stars. And that might be bright enough to cut through some of the light pollution that we're getting today. So let's see how that works out. Hades cluster is also sometimes known as MEL 25. So let's try that instead. Okay. What else is it known as?
Oh. I guess it has one of the first gas giant exoplanets found there? Is that?
Yes, which is super cool. Yeah, one of the first gas giant exoplanets found. Nope. All right.
Oh, apparently there are a couple of thin clouds. And Joanna says that in general, colors are the best way to tell galaxy age, I guess.
Oh.
Are you unable to find it?
Yeah, it's coming up in my list for some reason, which is weird. Well, you know what? We were going to do the double cluster. Maybe we'll do that instead. It's another open cluster. And I know that one shows up. So it's NGC 869. Let's try that one. Ta-da! Okay. Now this one's really high up. And as we look higher up, tend to be more clarity in the atmosphere. So that might be a good one to check out. And this might be one of the last ones we get a chance to do. Unless you don't want to do Ring. You should always jump in on that. Ring's going to be really colorful. So maybe we'll end off on the Ring Nebula before we get stopped. Because I know we wanted to look at one other planetary nebula.
Yes. End off on a high note.
End off on a high note. Ring was one of the first things we looked at when we had cleaned the telescope. So we had the telescope, the primary mirror on the telescope cleaned. I think we mentioned that last time that we were doing Starry Nights. Ah, there we go. Look at that. That is cool. Actually, you know, we can boost the resolution on this. Let's change the resolution one step higher. So what I'm doing is I'm changing something called binning on the telescope camera. And what binning does is it groups clusters of pixels together. And what that does is it cuts your resolution down, but increases the brightness of an image. So you kind of less clarity that you sacrifice for brightness. But if something is really bright, it's not really a step that you need to make. So you can instead go back to the full resolution of the camera. And usually things look a little bit clearer that way. One more time. Nice. There we go. That is a very clear cluster of stars. So yeah, this is NGC 869. It is an open cluster. It's located about 7,500 light years away in the constellation of Perseus. The cluster is about 14 million years old, so it's actually really young. I mean, that sounds like a long time in human lifespan, but this is quite young as far as space goes. So it's a very young cluster of stars. Open clusters are like kind of like birds that have just hatched. So these are stars that have formed. They've kind of blown away most of the surrounding nebula that has formed them. And now they are going to begin to spread out into the rest of the galaxy. And these clusters are located near a really big, what's called an association. It's kind of like a cluster, but it's a big collection of giant stars. In this case, it's called an OB association. OB are the most massive stars that we find, Class O and Class B stars. And this one is kind of associated with them a little bit through gravity. So these clusters are kind of moving along with another really large group of these massive bright blue stars in space. And so a lot of those bright blue stars are in the picture. There are a few of the tinier orange stars as well, smaller stars in this cluster too. And we're able to see those like distinct colors in each of them, which is really neat. I'll try to play around with the color here a little bit more as well.
Yeah, I think this object is kind of new-ish for me. I don't think I've ever seen it nor heard of it before, so I don't have a whole lot to say about it. But I do find it cool because it's a double cluster, I guess, but we can't see the other.
Yeah, the other clusters
right?
over here. Yeah, so there are two. You're right. There are two clusters. They're pretty close to each other in our telescope. They tend to be too large, too far apart from each other to be able to see individually, or together rather. So we do see them individually instead.
I think our telescope's just too powerful.
Yeah, for some things, the field of view, like, it's not ideal. That's why even having like a lesser powerful telescope is still cool, because you get better views on things that might be wider in the sky that you want to be able to see.
Yeah.
But our star would have formed inside of a cluster like this as well. We would have been part of an open cluster of stars that eventually spread out into the rest of the galaxy as the galaxy turns. And so, unlike the original cluster we looked at, the Hercules cluster, that is a globular cluster and it's very old. Those are very, very old stars that are close to one another, whereas these are younger stars that are beginning to spread apart from each other. So the globular cluster, M13, the Hercules cluster we saw at the beginning, those stars will never spread apart. They are gravitationally bound to each other, whereas these ones are going to be pulled apart by the motions of the galaxy and by other passing stars kind of heading off into space. So very young stars, only 15 million years old. And the whole cluster of them is about 33 light years across. So you're looking 33 light years across. You got this group of stars in there, all floating around through space. So those are stars being born. One more star dying. The Ring Nebula.
Yes.
Okay, let's do it. We'll end off on the Ring Nebula. It's very colorful. Hopefully, we get a good view of it. And it's
Yes.
we were being told that there's clouds rolling in. So hopefully, that's not where one of them is.
Okay. Yeah, I feel like we look at this one a lot, like in person when we're doing Starry Nights, but usually I'm outside talking to people and whatnot, so we look at it a lot. Maybe people that are watching or tuning in have seen it a lot, but I get excited because now I can see it.
All right. So here we are coming up on our last object, the Ring Nebula. Ring basically through the telescope. If you're ever up at the observatory, these nebulae, the energy, the light of the energy isn't enough to necessarily activate the color receptors in your eye. So instead, what you'll see is kind of more of like a black and white sort of smoky haze, and it looks basically like a ring of smoke in the sky. But we should hopefully. Oh, there's a thin cloud near the Ring Nebula, I'm being told. But it's possible that that we'll be able to see the color of it. So the color does pop to the camera, even if it won't show up to... Oh, yeah, it looks like we're looking straight into a cloud. We can see it in there. It is visible, but I think it looks like we are looking through a cloud. That's why we have this sort of purple hue all around. Maybe it'll move out of the way. Let's reset and try one more time.
Oh, poor Joanna.
Oh, that's a little bit better. Okay, so there we go.
Her fingers are cold as she's typing out stuff. Oh, look at that.
Yeah, we're not picking it up super well, but it is there. Let's see.
That is very pretty in my opinion. I don't get to see it very often. I feel like it's very, just like how easy it is for our telescope to like pick up on the light and whatnot. It's just so bright, I guess. But it's just always a treat to look at, I feel like, you know?
Oh, I love this nebula. It's really good. Yeah, and it's because it's so high in the sky, it's often visible throughout the entire year that you're able to see it.
Yeah, and it's also, another planetary nebula. There's that white dwarf in the center, which I think you can see right now.
Yeah, that's it right there in the middle. You can actually see the white dwarf there in the center. This one being closer, I think this is closer to dumbbell. It's 2,570 light years away from Earth. But the gases are expanding outward at about the same speed, so about like 20 to 30 kilometers per second with the white dwarf toward the middle. White dwarfs are really hot, like thousands and thousands and millions of degrees on the surface.
Yeah, I just feel like inside of a planetary nebula is kind of a bit of an oven. I feel like there's a lot of ionization going on, and that white dwarf is definitely still pretty hot.
Oh yeah, totally, yeah. Like and even brighter than the sun. So white dwarfs can be. This one is about 200 times the luminosity of the sun. Surface temperature, about 125,000 degrees on the surface. Probably even hotter inside. Mainly made of carbon and oxygen, and then you've got all that ring of material. And then, like you were mentioning, the colors in the dumbbell very similar here as well, right? You got that kind of green haze in the center, sort of red on the outside as the hydrogen expands outward into space.
Yeah. So you got the layers. It's very nice, yeah.
Do you think that there will be other civilizations checking out our sun like this billions of years from now?
Ooh.
When it looks this way?
Maybe. I feel like our star is isn't our star kind of average though?
I mean, yeah, but eventually yes, that is true. But it doesn't mean that eventually it won't become some beautiful ring nebula in someone else's sky. So, when it
Very
finally
true.
goes, maybe that's possible. Maybe that someone will be observing us in the future. I always wonder about that. Whenever I'm seeing stars dying and I'm like, hey, are we going to be observed like that in the future? Or, when new stars are being born, I always wonder, like, hey, maybe some civilization will be orbiting that star in 4 billion years looking off with its telescopes out into space. Wouldn't that be wild? Doing their
Wow.
own starry nights sometime from now.
Very, very trippy. Yes. Yeah, no, I think that like uh once our star goes, it'll when it's gonna be at its end of life, we're gonna see it like expand, like grow into like a red giant, right? So it's gonna expand and then it's gonna shed off those outer layers.
Hmm. Hmm.
So, and maybe the other civilization, when they look at our star and look at it being a planetary nebula, maybe they'll have a nicer name for the classification of nebula.
They've come up with a proper term for it rather than being stuck on like William Herschel's misnomer from back in the day.
Yeah.
They'll allow their astronomy vocabulary to evolve properly. Uh, that's cool. That's a very good point.
Yeah.
Well, listen, everybody, we love doing these shows. They are super fun. And we're very grateful that people are willing to spend their Friday night hanging out with us, either in person at the observatory or here online. We just have so much fun. We love all of you nerds who like checking out the universe and asking big questions about space and thinking about how there's stuff that happened and now we're here. And so please take the time to spend with us as well on site. So remember that we are open every Friday at the Trottier Observatory at Simon Fraser University if you're able to make it in person. We only operate if we think the skies are going to cooperate with us. So we post updates of that on our Facebook page and on Twitter as well, and by email if you're on our email stream. So make sure you sign up on our email list as well, which you can do on our website. And just Google Trottier Observatory. You'll find it in there. Maybe someone wants to throw it in the chat feed as well, where you can get on the mailing list. That would be great. And then you get firsthand information. Usually we try to announce by noon on Friday. I know that makes it tough for planning, but sometimes the weather can change quickly. So then we'll know usually by then whether or not we're going to be up there in person. And the last Friday of every month will be a virtual stream like we're doing tonight. So you can always clue into those. And if you miss a stream or if you know someone who might be interested, these streams stay on YouTube. So they will be here.
Oh no.
That's not a bad thing. No, it was great. We were great. I think we were great. We were great, right? We did okay. So they will be online, and you can always share them with people, and so you can always watch them afterwards as well if you happen to miss them.
Yeah, I just wanted to say this was my first one, so might have been a bit nervous.
I had so much fun with you. This was awesome. Thank you for doing it with me.
No, I think this was great. It was a lot of fun. I'm only kidding about it, it being recorded. That's awesome. That's great. Yeah, thank you. I wanted to say thanks to everyone for letting me talk here on here, and Matthew, thank you for having patience with me because this is my first time doing this kind of thing.
You were fantastic. I loved it. Thank you so much for helping me prepare and then checking out our target list and making a target list. Thank you as well to Kieran in the moderation feed and Zach, and of course to Michael from the Royal Astronomical Society, and then of course I think Milan from the Royal Astronomical Society also came on site. So I believe we have some members of RASC who are up there right now on site as well. So thanks to them for coming. And of course, all of the members of RASC who show up. So if you haven't been at one of our Starry Nights in person, it's not just the main telescope, but also a lot of telescopes that are brought by the members of the Royal Astronomical Society, their own personal telescopes that they want to share the universe with you as well. So while you're waiting in line, you also get a chance to check out those other telescopes too. So please remember to keep looking up. Thank you so much again. We hope to see you on another Friday night for Starry Nights. So this is us